Hi everyone, today we're going to be going over some basics of thermal simulations in SolidWorks. So SolidWorks thermal simulation walkthroughs and tutorials online are sort of vague, and there's honestly not that many of them. The ones that are on the internet are pretty old as well. It's just not something that's very, I guess, like well explained online. So this is only going to cover some basics of thermal simulation. And that's also why thermal simulation, I think personally, is one of the more difficult simulations in SolidWorks because of how vague and how and the lack of documentation for this simulation online. There's just a lack of documentation for the simulation in particular, I think. So we're gonna start by going over some thermal conduction calculations and simulations on the block on a very basic beam shaped block. But of course, it's not going to be it's not going to be made of beam elements, of course, because beam elements don't really account for thermal parameters, thermal conditions. So we're going to go over hand calculations as well to back up our simulation results to make sure we're roughly in the right ballpark, because it's always good to corroborate our simulation results to make sure that we're applying all the loads correctly, or roughly in the right places and roughly in the right amounts, and to make sure our assumptions are not like way too drastic. Finally, we'll also go over actually transient versus steady state real quick, because there's basically two types of thermal simulations. One over a long period of time, basically like steady state, right? It's over a long period of time. After a long period of time has passed, what are the thermal conditions of the block or object that you're looking at? And then transient, it's over a very specified period of time. So you can specify the period of time as well as the different intervals that you take measurements at, or you take simulation calculations at. Number two, we're going to go over real quick also a pretty simple example of thermal convection. Wait, excuse me, actually. Yeah, excuse me. Sorry, I just ate a banana. All right, so number two, the effect of thermal convection on a tube/pipe. So this might be relevant to some of your projects because many biomedical instruments involve some sort of piping or tubing to like transport fluids or even gases, you know. And this will also be backed up by some hand calculations. So we can also make sure that the value we get in the simulation is in the right ballpark of values, right? To make sure that our simulations are not too unrealistic, and to make sure our calculations, I guess, and our assumptions are, again, not too drastic. And lastly, we're going to go over thermal simulations using assemblies, which is similar to other simulations on assemblies, requires a little bit more constraints, a little bit more conditions, right? And those conditions are basically the interactions between those individual parts. So in this case, we're going to look at some local interactions, more specifically resistances between heat resistances between different surfaces. And we'll look through a pretty cool example, I think, regarding this. So let's start by looking at the effect of thermal conduction on the block. So let's move that around. Okay, so in this case, I think it'd be easier to, here, let's look at the model first. So this is something that I just quickly whipped up. So this is 0.25, it doesn't really, it's not very clear, but it's 0.25 inches. So it's a square, the cross section is a square with 0.25 inches on both length and width. And that is extruded a distance of 5 inches. So it's a pretty small beam / stick. And I set the material to just plain copper. As you can see, there's different types of coppers. There's chromium copper, there's beryllium coppers. I just chose regular copper, and here, it's pretty important. In here, we're gonna need this value here, the thermal conductivity value. So we're gonna need this to calculate roughly how fast, I guess, heat conducts throughout the material. All right, so we're gonna need this number here. So either write this down when you're doing the calculations, or just take a screenshot of this. Take a picture of this. Unfortunately, I don't think you can. I don't know if you can copy and paste this actually. Copy. Oh, you can paste it. All right. So you can just copy and paste it, I guess, as well. All right. So let's quit that. So the first simulation I did. So the way I did calculations to validate, I guess, to validate my simulation is here. Let me show you guys. Should I do calculations first or should I do simulation first? Here, let's do hand calculations first. Get it over with. It's we shouldn't spend much time on it. You guys can take a look. I'll put it in the modules page after class sometimes. Hopefully right after class or as soon as possible after class. So here is a slide from a lecture. So here is a heat conduction heat transfer equation, a simple equation that we can use to calculate heat transfer via conduction, right? So it requires Q, which is the heat load, and that will be what we're calculating here essentially. And then we'll be given, so we'll need temperature at on both ends, as well as the length and the cross-sectional area of the beam itself. So as you can see, this is a very simple example because it's just a beam. It's a very simple shape, first of all, and heat's only traveling one way, and there's only one type of heat transfer, and that is conduction. So again, just like the job tests, I put all the numbers into a nice Excel document or Google Sheets. So you can set up these macros, I guess, or these functions almost to automatically calculate the heat output based off of the other parameters you enter. So in this case, we're gonna we have all these parameters except for the ending temperature, the temperature on the other end. The temperature, oh sorry, this one right here, T1. We have T2, which is just room temperature in this case, or around room temperature. And we specify T1 as essentially, yeah, okay. So we just specify T1 as something that you want. So in this case, I chose 100, I chose 99, 95. This is one of the values I played around with. So given these 5 variables, we can then plug these into the equation and then get the heat load. All right. So the reason why I want to go over this first, the reason why I want to go over these calculations first, is because we're going to actually use this heat load to see if we can replicate these 2 temperatures in the simulation. So to clarify, I guess I chose these 2 temperature values to see if the calculated heat load when applied in the SolidWorks simulation can give us these 2 heat loads back, these 2 temperatures back. All right. So mainly we'll be focusing on whether or not we can get T1. We can get the T1, the result for T1 in our simulations. So I'll be doing 3 simulations given like slightly varied lengths and areas, lengths and cross-sectional areas, as well as I guess the T1 temperature value. So we'll see it later on if the values match. Again, you also want to specify your simplifications. For example, like it does not take into account the other types of heat loss or heat transfers. So that's something I mentioned earlier. Again, I also use a square beam, which is probably one of the simplest 3D shapes you can model with. That's why, honestly, with thermal simulation, because it's more difficult and more confusing to work with, if you don't apply the loads and different conditions and very specific manners, right, it won't give you like a proper result. even if you flip an arrow, for example, flip it the heat direction, you get completely different results. And sometimes you can spend quite a while trying to figure out like what's wrong, especially when you have too many heat loads or too many conditions. So you want to basically apply thermal simulation to simpler models, to individual parts. That'll be the easiest. Or with assemblies, if you had to do assemblies, very simple assemblies. So the simpler the better, essentially, with thermal simulation. Otherwise, it gets pretty confusing later on, and the hand calculations gets very, very ugly. But again, if you guys can do it, it's all up to you. Go for it. I encourage you guys to branch out and explore the limits of thermal simulation. And finally, we assume that there's even heating, even heat transfer throughout the entire beam, and even heating on the other end. All right, and the source is the lecture PowerPoint here. And this is from SolidWorks. So I guess we should also put SolidWorks in here, but obviously we're using SolidWorks, so that's assumed. All right, let's go back to SolidWorks. Copper beam. All right. So when you first start a new thermal study, it's very similar to the other ones. It's actually exactly the same, except you hit thermal study instead of static or fatigue or drop. So where is it? There it is. It's right above buckling. Once you hit check, well, you should name it something that's like intuitive. Like in this case, because my file is copper beam, I named it CU beam. CU is just an element name for copper. So this way I can find the files if I ever need it. I can find the files more easily. I can find the files associated with my simulation more easily. Okay, so I already made 3 simulations already because it's easier if I just show you guys how I did it and the results I got instead of trying to get it live, I guess, because I do change the shape quite a lot. So you will hit check here, and then you will bring up this new side panel that you're probably really familiar with by now. So instead of your typical loads, you have thermal loads instead. So first of all, remember what I said about this thing, how there's transients and steady state thermal studies. Wait, sorry guys, I'm gonna pause the recording real quick. I have to blow my nose. All right, guys, I'm back. All right, I was down bad, guys. I was down bad. All right, so it's transient versus steady state. Let's see how this works, right? So first of all, to choose either transient or steady state, you have to go into properties for your simulation model. So in this case, it's this selection right here. So right click on this thing and hit properties. As you can see, it's always going to default you to steady state. So if you just don't touch this thing, if you don't touch properties, let me show you again. So right click on this top option here, properties. So if you don't choose, if you don't go in here to specifically choose transient, it'll automatically default to steady state because that's typically the default, and it's just more useful, honestly, because you want to see how heat affects it over a very long time period. Usually, it's rare that you only apply a heat source for like a few seconds, for example. It's most likely that you're applying the heat source to your material or to your part for many minutes or even like hours. So that's why steady state is the default. All right, but you can choose transient, and then as you can see here, you can choose total time and time increments to calculate your for you to do calculations at, but that's for later on. I'll show you guys in the assembly thermal simulation. So if you do that, make sure your material is selected as always. Material is pretty important. If it's not selected, you can't really get proper results, or I think just doesn't let you run. So for mesh, go with typical mesh. Just create mesh, and then you can choose the mesh density. Excuse me. Usually it'll choose the most appropriate one for you. I didn't set this to like ultra fine like this, but depending on the size of your part or assembly, right, you'll choose finer or coarser, more coarse meshes, more coarse mesh densities. So more coarse mesh densities mean that chunks are bigger, the discretized chunks, elements in your parts are bigger. So if your part is very, very small, right, they can't really split it into large chunks. They'll have to use smaller chunks. So they'll have to divide your thing up into smaller chunks. And always make sure that, like, I guess you can make sure that you can get more accurate results by choosing the appropriate mesh parameters. You can choose a curvature base if you're doing where you want more like dome-shaped, bowl-shaped, circular, curvature-based. Even like tubes, I guess. Tubes and pipes. You'd use curvature-based mesh, but it shouldn't matter too much. It's an option for you guys. You can play around to see which one's more accurate, or if the results differ even that much. So, oh shoot, cancel. All right, cool. I canceled because I already had a. Oh no, I ruined it. Oh, wait, can I Control Z? No. Ah, shoot. I messed it up. Oh my God. All right, so I want to redo this. Whatever. I'll fix this for class, but let's just skip that example for now, because it takes some time to, you know what, screw it. Let's fix it real quick. So let's go back into, so I started out with a beam of 0.1 inches on all sides and a length of 1 inch. So let's do that. Back to model. Oh shoot. Find the model. Okay. Change that to 1.1. As you can see, my initial thing was even smaller. That's why the mesh density was very, very low, because the shape that I started with was very small. I was looking to do like a pin, less of a beam. So this is more like a pin than a beam. Sort of a misnomer here, like a misnamed part. And then you can do box extrude, change that to 1 inch. So what I'm doing here is, every time I start, before I start a new study, I did 3 studies on 3 different components, right? But the component there's only one component, essentially. So once you do a study with one component and you change the component, you can't really go back to redo the same study with the same components. It'll only restart it. If you restart this study, it'll only apply to the current model you have in your models tab down here. So there are different tabs. 3D view, this is not very used. Motion study is pretty cool. You can play around with it later on. It's cool to simulate motion, to see how, for example, your gears work together. It can be pretty cool, fun to play with. So, and there are your 3 thermal simulation tabs at the bottom. In this case, I started with a model, I did a study, changed the model, started a new study, finished the study, changed the model again, and did the 3rd study. And thus the model ended up with the 3rd studies, the 3rd simulations model. So only the 3rd simulations model matches the current model I had previously before I changed it. So now I changed it back to model 1, simulation 1's model, and now I can remesh. Unfortunate, but what can you do? So remesh, check. Oh, so in this case, that was enough. The mesh didn't have to be that fine. You can usually just go with default. They usually get it pretty accurate. So here's the mesh. It's pretty cool. Okay, so let's now run the study. Actually, let's finish this first. Connections, right? For connections, you don't really need to bother with this for singular parts, for individual parts, because there's no interaction between parts. So no need for connections. And now for thermal loads, this is the most important part of thermal studies, because instead of applying forces and like torques and stuff, you apply thermal loads, thermal forces, right? So in this case, right click, you see your options here, temperature. That's setting a fixed temperature on any surface or edge or corner or points, right? Convection, which is like transferring heat through like movements of bodies of fluid basically. Heat flux, I think it's just general like general heat energy being it might be a combination. I'm not too sure exactly what this is. I think it's a general combination of heat being of heat leaving or entering the system. Heat power is you're actively applying a heat over like heat per time on a side or an edge or a corner. So you can apply all these to a side or corner or an edge. And then radiation is transfer heat through like electromagnetic waves. And this is honestly the most confusing one. I haven't touched this yet. I've touched the other four. I don't really play with heat flux that often either. I stick with heat, power, convection, and temperature in general. And these selections are slightly different sometimes if you choose transient. So if you do temperature for transient, it's slightly different than temperature for a steady state. And I'll show you guys later on what I mean by that. So if you want to add a temperature, just click temperature and then choose the face you want. In this case, I'm pretty sure this face. As you can see, you can choose an edge, you can choose a corner, but in this case, oh yeah, I chose this face. So I will click on this face and click check, or set the value first. In this case, 75 degrees, which is what I said in here. My one face is 75 degrees fixed. And my other face will have my heat power, right? So right click, hit heat power, and you choose your wattage, or you can change your measurement unit system and choose the appropriate heat input. In this case, I used BTU per second. BTU is the imperial system for power, essentially. So this 0.00313, that value is what I got from my calculation, actually. See, pretty cool, right? So applying this to the other end, I'm seeing if I can, obviously, this end will be 75 degrees or around 75 degrees, right? But the other end, I'm looking to see if that will end up being 100 degrees, essentially. So see if the simulation roughly can be validated with this, with these results and with this formula here, or if the calculations here can be validated by the simulation. Either way, you know. So in this case, run simulation. So once you have your property set up, you run simulation. It isn't. Okay, that's what happened, but I think because I have a different folder open associated with this. That's super weird. I never had this happen to me before. It shouldn't matter for now because we got a result. It's just not saved, which is fine, whatever. You can always rerun it. So in this case, you see here on the Fahrenheit, you can change the temperature value here by double clicking on this chart, double click. You see the right, the left side changes. If you go into the definitions tab, we're currently underneath the chart options tab. If you go into the definitions tab, you can choose the unit, Celsius, Kelvin, Fahrenheit, the three mainly used temperature units. All right, so I changed the Fahrenheit. I'm pushing defaults to like some other one based on your page units. In this case, 100 degrees on one end, 75 degrees on the other end. Let's go back to our calculations. There we go, 100 degrees and 75 degrees Fahrenheit, F for Fahrenheit. I couldn't get the degree sign, but F for Fahrenheit. Now those are the other two. I already did the simulations for you guys, so let's just take a look at it. If we go back to the other two. So I named it cover beam thermal 1. In this case, double click. Okay, so if you don't be an idiot and freaking try to remesh the whole part like me, you don't have to rerun the study for it to have the study saved. Control S. Always make sure to save your process throughout, because you never know when SolidWorks will crop out. Again, I emphasize this a lot because SolidWorks is very inconsistent. You never know what will push it over the edge, or whether or not like it had a bad day or some stuff. And if it had a bad day, it might just crap out on you for no reason. In this case, this is not my original shape, you see, but the results are saved because of all the extra freaking annoying files it generates in the folder. So I'm going to the folder where I keep my simulations. simulation practice, thermal simulation, thermal sims. So in this case, straight beam, all these files appropriately named, as you can see, thermal 1, thermal 2. This is why I say that the naming sort of matters, because it helps you differentiate. If you want to isolate these files, you can put them in a separate folder without separating them from, without confusing them with the other files, because there's a lot of files. Essentially, these files are the results. And that is the reason why we can call back to the results and have it show up again, despite having a different model. See, our model is much smaller than our model for the second simulation we did, the second thermal simulation we did. So in this case, we did different shape, same temperature, same heat power on one end, on one end heat power, on the other end temperature. Results, we got max of 79 degrees, low 75. Let's collect the results. Oh, whoops, I already had that up. So here, 75 and 79, we get 0.0013, which is the heat load we applied. And this will, as you can see, the same thing will happen. Same thing will be true for our last study, which I'll just show you real quickly. And it should also be saved, despite it being a different shape. If you double click it too fast. All right, so there's some issue with this. You're gonna have to change shapes and remesh it. I suggest this if you're gonna do, I'm only doing this to demonstrate, right? But if you guys are going to do different simulations on different parts, you should just make a new file. Don't do what I did here, because for some reason it has trouble saving all the individual files and distinguishing between saving the different files. So it cannot bring up the old results, even though the second one worked. What the heck? This one works. This one works. It's just third one just doesn't want to work. All right, I'm not gonna bother with changing the shape. I'll change it later and see if we can get it to work before I go to class. Now let's move on to the second part. So we went over the effects of thermal conduction on block and hand calcs to back it up, some transient versus steady state explanation. Let's move on to the effect of thermal convection on a thermal conduction on a tube or pipe, and some hand calculations to back that up as well. So let's do hand calcs first. Get the annoying stuff out of the way, you know. All right, so I typed it conveniently, tucked in the second tab down here, boom. All right, shifting to different gear now. So this is slightly more confusing. Typically you'll have, for assembly at least, or even for a regular part, you might have both conduction and convection. You want to look at both. Excuse me. But the hand calculations for that would be much more difficult. Would be more difficult as well. But I'm not the best at this. Again, physics is not my knack. It's not my strong suit. I can manage. So this is why I went with as a basic, simple example. You guys, by all means, should go off and explore around and see if you can do better. Hopefully you can do better than this. Okay, this is a pretty simple and lazy example. All right, so in this case, we're going to look at Newton's law of cooling. Essentially, this is the equation for convection derived from this Newton's law of cooling. So in this case, Q equals H times A times change in temperature. So Q is heat transferred per unit, which is similar to heat, which is very similar to heat load. So this watts or BTU per time. I actually don't know what BTU stands for, but it's some energy units, you know. All right, area is the area that convection will occur to, not the cross-sectional area in this case, the area that convection can take place on. So in this case, we're going to look at the entire surface area pretty much of our tube. All right, H sub C is a convective heat transfer coefficient of the process. So this value you had to find basically. This would be calculated too, but for basic fluids like air, like static air, air that is not moving, you can probably just find that online. Here I just found the gases at atmospheric pressure inside and outside of tubes are between 5 and 35 based on the other conditions of the environment. So I just want to put the average 20. Okay, so as you can see here, HC value is at 20. I did the exact same thing as conduction. I set up the table values and set up some functions so you can automatically calculate the heat transferred and then the heat flux, as well as the area based off of what you enter for the tube radius and the tube length. So here for the first example, so this is a constant value that won't change because we're going to basically like pretend like we're testing this in the same environment. Yeah, pretend we're testing in the same environment, but we're going to alter the radius and the length values a little bit. However, that shouldn't. We're still going to look for. We're going to be applying the same temperature from the inside of the tube. Essentially, I'm pretending that what's inside the tube is blood, and blood is roughly, I think what I read was like 98 point something degrees, which is roughly, which is roughly 310 Kelvin. When converting to Kelvin. So 98.5 degrees, I think, is the temperature of like human body or blood. And that's roughly 310 kelvins. And I'm comparing that to room temperature, which is roughly 298 kelvins. So in this case, I convert everything to imperial, make sure your units are consistent before you do calculations, otherwise they won't be accurate. So it'll make sense that the the heat values will be, the heat transfer will be different given the different physical dimensions. So as you can see, the smaller, wait, this is actually, I'm missing a value here. There you go, I'm missing a 0. Oops. Okay, that makes more sense actually. That might have screwed up my calculations a little bit. Wait, I had 0.25 previously. Okay, so I changed this value a little bit, but I used heat flux, the estimate for heat flux, as my SolidWorks input. So in this case, I did calculations first and then use this as my SolidWorks input. So technically, I'm like validating my calculations with SolidWorks as opposed to validating SolidWorks simulation with my calculations. But I think if you can do it either way, to be honest, you're corroborating your results either way. So either way, I think should be fine, as long as the results are roughly in the same ballpark. So let's move on. I'm going to test these parameters. You can take a look at it. I'll upload this document hopefully as soon as class is over, or as soon as possible after class. As you can see here, given the fact that we fixed the inside temperature and the outside temperature, the heat flux per surface area is the same. So I'll be applying 240 in the heat flux value in SolidWorks simulation. I'll show you guys very soon. But again, simplifications. I won't read these out loud now, but you guys take a look in the sources. These are pretty useful for calculating thermal coefficients and understanding what thermal coefficients are and what they do, and basically understanding Newton's. I pulled this snippet here from the websites, so it's pretty useful. I found it very, very informative. They also have an online calculator too, I think, for you to calculate these values. I haven't tested it out yet, so I'm not sure how accurate that is. Probably more accurate than my calculations though, but you know, okay. So let's see, 240, right? For all of these, essentially we're plugging this value in. We're plugging this value in. No. But yeah, we're plugging this value in, we're plugging this value in, this value, and this value. All right, so let's go back to our simulation. So I also did, hopefully these will work. Hopefully these results are saved and it won't crap out like the beam. But as you can see, I put, if you I basically did the same process with starting a new simulation. This is also a steady state problem, a steady state simulation. So again, no connections, material, make sure it's the right material. In this case, I chose PVC, which is apparently a pretty common material, common flexible material for medical devices and medical tools / items. No connections because it's just a single part. Thermal loads, I chose temperature. You can make these show up or not. These things will, the symbols here will be colorized if you hit show, and they will become black and white if you click hide. It's pretty cool. So I hit all the arrows, so it's more, it's easy to look at and understand. So in this case, we'll have a tube here. The color doesn't really matter. You can change the color if you want. So here I have temperature set to temperature, right click, edit definition. So temperature here, I'm setting the inside temperature to 310 roughly Kelvin, and that's simulating essentially blood. It is on simulating here, simulating blood, filling up this tube, and essentially I'm assuming to start, the temperature on the inside and the outside surface are the same temperature as the fluid flowing inside of it, flowing inside of the tube. So roughly 310 degrees Kelvin. So inside is 310, and the outside to start with is also 310. And then for convection here, convection coefficient, actually, I think I had a small hiccup here. So here I used actually 10 as the coefficient. So let me just quickly change these, just somewhat change the values here a little bit. All right, so the heat flux is now 120. Actually, I don't think we'll, nuts. I did screw up a little bit. Well, thank God I found it here and not elsewhere. Okay, so I messed up here a little bit. The heat flux value should be 10. I chose 10 for some reason, but yep, but just have to make do now. So 10, and then for the ambient temperature, I set as the room temperature. Ambient temperature, bulk ambient temperature, I set as the room temperature. Convection coefficient, I chose as the lower end of the range that's possible for air. And essentially it's free convection as well. Going back to this page. Basically, based on the different conditions, such as whether or not it's like free convection or forced convection, the rates are higher or lower, because when you're forcing convection, such as like blowing, like using a fan to blow a tube, it helps the fluid take away heat much faster. So obviously the heat transfer coefficient will be much higher. So in this case, we're just looking for the free. So as in like the air is basically still or near still. Okay, so let's go back to our simulation. So the first one I did convection on the outside. So if you right click, convection on the outer surface, temperature on the inner surface, and heat flux. So in this case, I right clicked and hit heat flux. I selected the two flat surfaces at the end and set to 0. Essentially, that is like insulating the tube. There basically there shouldn't be any heat lost through the sides here. Although I don't think this should matter too much. Can honestly make do without this. I just added it, and it seemed to work fine for me. So I just kept it in, but you guys don't really need those, I believe. The results shouldn't differ that much because the surface area is so small anyways. But yeah, you can basically make any parts to be insulated by just setting this heat flux to 0. So that might be something you want to consider. Having some surfaces where there's no heat loss. We're assuming some surfaces have no heat loss. So this is one of the assumptions I made as well. And that you should include in your proposal or in your results section. So mesh plot, you create a mesh, and then you run the results. You run the simulation, you get a max of 310, which makes sense because the inside should be the same temperature as the fluid that's flowing through it, 310. And then as you slowly approach the outside, it cools off a lot more because of convection and because it's further from the source. The lower end is 305 roughly. So 305 to 310, right? Again, you can also right click and hit ISO clipping or ISO or section clipping to get a section of the view, or you can get, you can see here, oh, this happens when the thing is too small. So there you go. That's pretty cool if you need this. Look at the cross-section heat distribution. Also click ISO clipping. And so bring down the limits. Or rather bring up the limit so you can slowly remove parts of the tube. As you can see, as we bring the limit up, we're only keeping that upper end. So as you can see, this is everything from 309 Kelvin and above. It's on the inside roughly, near edge, in the inner face of the tube. So that's pretty cool too if you want to see where the thermal loads are highest or lowest. Again, you can also turn on these little ribbons here by just double clicking this. Takes a while, and by hitting or hiding, unchecking or checking the show min and max. I'm gonna hide these for now. All right, so let's go to tube number 2. So in this case, I applied the heat flux value that I got from my calculation, which is not supposed to be 240 actually. So it's supposed to be 140 due to my mistyping. But yeah, the temperature on the inside is still the same, and the heat flux on the two surfaces on the edge are also the same as the previous study. So I legit just right-clicked, copy study, and changed a few things. Basically removed the convection and put in a heat flux value. And in this case, I'm trying to see if I can replicate the temperature results. I can replicate the convection results using heat flux and our calculated heat flux value. So essentially, it's sort of weird. We're validating SolidWorks by using SolidWorks, inputting our hand calculations. So we're getting down and dirty here a little bit. But in the end, it's still, as long as you corroborate something and make sure it's in the right ballpark, it should be fine. Again, this has to be completely accurate. So, and always like make that, add that to your assumptions and in your simplifications, because we're not at the point where we can do every single thing with a T, to the T, right? Like we can't add in all the different components, all the different loads. So we have to make sacrifices, and those are the simplifications. But we have to make sure to write them down and to note them as possible factors that can impact our results. All right, so our thermal load, our temperature, as you can see, should be going from 310 to 305 to 310. But because our heat flux is much higher, it's losing much more heat. So the temperature down here is low. It should be higher, essentially, because I made the mistake of putting in 240 instead of 140 here due to the mistake I made in the calculations. So let's redo that actually. Let's redo one of these calculations. Let's redo one of these heat flux calculations. So we're going to tube, the first tube. My third, so every pair here is a trial essentially. It has different parameters, but they belong in the same, I guess, same study. So here's the third one. Again, same coefficient here, different dimensions for the tube, different area, same temperature. We're aiming to get the same temperatures. And here the flux is the same. It's 120 actually. Oops, not 140, 120. We halved it. So 120. So here, let's put the model first to see if our model is the same as our, yep, okay. So I kept the model from my third simulation. So we can just rerun this without fear of overriding our old results. All right, so let's check out thermal. So this is fine, right? Because this is not dependent on our flux. As you can see here, this is going from 307 to 310. 307 to 310, okay. So because the tube is so much thinner, I guess the heat transfer, the overall temperature of the tube / pipe is just higher overall because of how much closer it is to the source. As you can see, oh, that's cool. All right, So let's corroborate that real quick. So instead of doing 240 here, edit definition, bring up heat flux, you can choose the units, make sure that the direction is correct. The pointy part of the blue shape here is the direction that the heat flux is traveling. Essentially, is traveling away from the tube. You don't want to travel into the tube because that's heating up the tube while you're also heating up the tube from the inside, which doesn't really make sense. So you want the heat to essentially escape, but you want to escape at the rate that we calculated to see if the temperature on the outside is the same. Because the temperature is the same, that means the heat, that means this convection rate, that means this heat flux value matches the convection value that SolidWorks simulation has given us in the prior simulation. So 120, reverse direction to make sure the arrow is pointing out, make sure the heat is leaving the system. Okay, hit check, or hit X because I didn't make any changes to it, but we do want to, oh, no, we do want to change it to 120, whoops. 120. All right, heat flux, again, I set the two ends to 0, heat flux of 0. So the two ends are essentially insulated. Although it shouldn't matter in this case because the surface area is so freaking small. But for you guys, again, it might matter. So then you can run the study. Sometimes, again, when the mesh is, there's going to be a pop-up menu that says like your mesh is failed because for some reason, right? Your mesh failed for some reason, and that's mainly because hey, what the heck? Oh wait, I suppressed this for some reason. Okay, we're gonna have to rerun this real quick. So when there's a error pop-up that tells you like mesh failed, for example, you just have to go to your mesh, and typically it's because your mesh value is set too big. All you do is make the mesh setting, mesh density, set that to a finer value, and you should be fine. So in this case, we get 306 to 310. So that's using the hand calculated heat flux value, right? Going back, 310 and 300, oh wait, 295. Oh, this is ambient temperature. So we're actually comparing with the other study, not with the Excel, not with the sheet document. Going back to SolidWorks. So in this case, it's going from 306 to 310 using our own flux value, heat flux value. But if you use the convection calculation, you get 307 to 310. So this is around the same ballpark. So we can, it's corroborating the results here a little bit. We know that we're roughly in the same ballpark, we're roughly correct. Our assumptions are somewhat viable. I call this a success. The other two here are the same, except again, I messed up at setting this heat flux value here. So these results are a little bit off. I'll have to change this and change this heat flux value as well as change the tube shape dimensions so I can rerun the study before class starts. So that would be more accurate in class. But yeah, essentially the heat values you get for each pair should be roughly the same because our hand calculations are based off of the values, also based on the values we input for the convection. And this, again, everything's in here. Definitely take a look at these links and this function and these data results. All right, so now that we've been over the thermal convection example and some hand calculations to back it up, let's go over real quick thermal simulations using assemblies. That's like more complicated, and what local interactions we need to keep in mind of. We need to be mindful of. Okay, so let's see, going here. That was while I was burping. Also, this thing is like a sleeper, by the way. Coke with coffee. it's an interesting flavor. If you haven't tried it, highly recommend it. Even if you dislike it at the end, it's good to try these crazy flavors. I never thought I'd taste Coke with coffee. All right. I also want to taste mango Pepsi, but I haven't get my hands on. Haven't had the opportunity yet. But it sounds pretty good too. Pepsi with mango. Okay, whatever. So here I have my 3 parts. I can drop these into the module if you guys want for practice. But essentially, we're doing heat thermal simulations with assemblies. You want to first make an exploded view. So the reason why you want to make an exploded view is because instead of having to suppress everything, suppress individual parts to get to the hidden faces, essentially, right? The hidden planes, the hidden faces, you can just explode the view. Typically, these will be exploded too, but we're assuming that these are just connected with the block. So there's if you're planning to put something between the 2 surfaces, such as like something we'll get to eventually, the local interactions, you want to be able to separate them very easily, and that's like the best way. And doing an exploded assembly is the best way to do so, to quickly toggle between being able to access these services and having it go back to its original assembly, its original structure. Okay, so let's do comp chip. I don't think it matters which one I do. I'm pretty sure the second one is better. All right, so they're the same, I think. I think the first one is what I worked on. So there's actually a YouTube video on this, which I think is pretty cool. You can just look up thermal simulation example, and it'll show you how to do this example. I made these parts. So if you want these parts, just let me know. I can just send it to you real quick. But it's very simple. I just want to show you guys real quick that you want to add on top of everything else. So here they had heat power from well, in this case, this is supposed to be like a chip, computer chip. So this is a processor, I guess. So that would be the main heat generating source. So there's a heat power of 35 watts coming out of, essentially the chip is 35 watts. So the heat generated will be roughly 35 watts as well. All right. There's gonna be convection from the bottom plate here, as well as convection from the chip itself. So again, convection is just heat loss or heat transfer through the air. So essentially, the heat transfer will come from the block, right, into the flat plate here, as well as into these 3 pins. But there's also going to be conduction between the chip and the plate. So the plate will also heat up, and the plate will have enough heat that it gives off a significant amount of its own heat in the form of convection. So this convection for the plate, convection for the chip. These pins will also have some convection, but they're very small components, and that's not really the focus of this simulation. They can do that as well if you guys like. In that case, you also have to explode these, well, pull these apart as well in your exploded assembly tool. And you guys should know how to do that already. You can explode assembly. So in this case, going to scroll to the top, look at the right click on the simulation component title, go to properties. So now, as you can see, we toggle between the 2. In this case, it's transient. We're looking at what are the effects of these loads over 300 seconds, right? Having SolidWorks do calculations every 10 seconds for us. So have SolidWorks look at the heat loads and the heat distribution after every 10 seconds until it hits 300, right? Or until it finishes 300. It finishes I guess it's the 30th or the 31st calculation. All right, so all you do is change these values, just ignore this, and then hit OK. So in this case, remember how I said based off of whether you chose transient or steady state, some of the variables, some of the parameters here changes. Well, what I mean is you can now do initial temperature instead of just a fixed temperature over a steady state. right? You can do fixed initial temperature. So it has a starting point. Essentially, if you don't give SolidWorks thermal simulation enough parameters, if you don't give thermal simulations enough parameters, it cannot enough boundary conditions, right? So you guys know what you should know what this is already because it's in 371 and then most math classes, but you calculate most things from those boundary conditions, all your critical values and all these things. And SolidWorks basically does that for you, but it needs those boundary conditions. And so a boundary condition is the initial temperature usually. It starts out at a certain temperature. In this case, 25 degrees Celsius, which is also 77 degrees Fahrenheit. So this is just room temperature, the default generic room temperature, 25 degrees Celsius. So hit check. Okay, so it was already 25 degrees Celsius. Heat power, we said 35 watts. And convection, they set it to a value within the range. So as you can see here, right click. Well, even without right clicking, if you just hover over it, it'll tell you convection coefficient. Oh my God, excuse me. Okay, this Coke with coffee is really getting to me. All right, so even without clicking on it, it'll tell you the convection coefficient is 25 watts with the fancy units. And that's still between the, remember I showed you the free convection coefficients of air. So that's still within that range. So there's some leeway here with this. This is an assumption, this value is an assumption you'll have to make as well. Unfortunately, it's sort of an experimental thing. So these are both 25s. We're just completely ignoring the pins because of how small they are, I guess. But you can definitely consider the pins as well. And then heat power from the block. If you right click, right, it's just selecting all the faces that are on this block. You can just choose the component that you want to include. So if I want to include the entire, 3 pins, boom. Wait a minute. Oh yeah, I patterned the single pin into 3 pins. So I need to click this as well, or these 2 as well. That's how you include entire objects instead of having to click on all like 5 faces of this thing. So it saves you a lot of time. We can select all exposed faces and that will choose all the faces that you can see. So we do this case, boom. So, if you click on exposed faces, it'll select everything you can see. And then you can do that and then deselect the ones you don't want. That's also one approach. So I'm just gonna leave this be, mesh it real quick, and then you run the results. You run the study to get the results. And this is what you get. As you can see here, because the plate, oh, actually, I'm gonna tell you guys. So the unique thing here is the connections, right? Now there's global interactions. You leave this be, okay? Just don't touch the component interactions, global interaction, bond and mesh independently. Just leave this be, okay? But this local interactions, you can right click on local interactions. I don't know why it still brings this up, but hit local interactions. And essentially what you can do is click on 2 surfaces that you want to have a thermal resistance with. For some thermal resistance, you can either set to have very high or very low value. In this case, because this is a chip, right? We can pretend, for example, that we're using some sort of computer paste here, right? Some sort of thermal paste to help with heat transfer, right? So usually with thermal pastes, they give you the thermal resistance value, Kelvin per watt, right? They'll actually give it to you in the description somewhere. You can just enter that very low value with a pretty low value into here. In this case, we set it to 0.0032 kelvins per watt. So it's a pretty low value because thermal paste helps it conduct heat much faster into this plate. That explains why the plate is so much warmer than the pins. Actually, oh, just kidding. The pins are pretty hot too because they're also very close to the heat block and they're smaller. But all right, just ignore what I said. But essentially, you can choose different thermal resistances between different surfaces, different components. So you can make some components less conductive than others, or even less conductive than others. If you use some sort of connection, some sort of paste in between, some sort of adhesive in between, there's going to be there might be increased or decreased heat resistance between the two. So if you want to change that, you choose your local interaction and put in the proper thermal resistance values. So you can do that between any two surfaces pretty much. And that should be it. Oh yeah, as always, with these plot steps, you can see the max temperature and how the temperature shifts over time. As you can see, it starts out pretty hot because we set the temperature. Oh yeah, with the power output to 35 watts. So it starts out with with most of the temperature contained, right? But as you can see, it immediately starts conducting. The pins immediately start to conduct heat as well as the plate. But the plate has slightly more resistance than the pins. I believe it's 0 by default, so that will explain why the heat goes into these pins faster. So as you can see, heat is also being conducted into this plate, just slightly slower, but heat is being conducted. That's why it's so much cooler in the bottom here. As you can see up here, there's no conduction, right? There's only convection. So heat escapes much slower, which means it should be hotter up here. And it's more red up here, so it is hotter. So you can look at different steps. The last step. So this is what it is after 5 minutes. Again, this is not steady state. Steady state, you would require a different set of, you have to change the temperature again for steady state. It works slightly differently. In this case, steady state might be a little more difficult, but it all depends on what sort of loads you want to put on the chip itself and where you want to put the loads. So this is not really applicable to what you guys are doing per se, but I'm just trying to show you guys that you can add thermal resistance between the two components to either make it easy to conduct or hard to conduct based on like other factors you have. So that is pretty much all I have to discuss, I think. Again, you can also do ISO or section clippings. So in this case, ISO clipping would be, I feel like, more applicable. As you can see, okay, there you go. You can slowly isolate the area with higher temperatures. There's the highest temperatures up here. The parts are the hottest. All right, cool. Just a recap, went over real quick the effects of thermal conduction on a block and a very simple example of how transient and steady state studies differ, how they differ, hand calculations to back up the thermal conduction study, thermal convection study on a tube/pipe, and also the hand calculations to back that up. And then also looked at thermal simulations and how that differed because it added in local interactions. So hope this clears a little bit, hope this clears things up a little bit with thermal simulations. It's one of the more confusing ones for sure. I honestly struggled with it, and I'm still struggling with it a little bit. Just to play around with different loads, different conditions. Again, if you don't have the boundary conditions, it will fail on you. If you just set the temperature to one face of the block, it might fail on you. Or if you don't set, most likely you won't set, you'll forget to set temperature, and the block will fail on you because there's no boundary conditions. But the simulation might fail many times before you get it right. You just have to play around with it a little bit, and yeah, good luck. And take care, guys. Take care. Let me pause recording.